problem 10, we've got a couple of capacitors in series with a resistor and a switch, and I plugged in all of the values already, but it tells us the first capacitor is already charged with 120 volts. The capacitor 2 does not have a charge, so when we close the switch, the charges are going to flow from capacitor 6 through the circuit. Now, the next thing we want to think about is what it means to be in equilibrium. When it's in equilibrium, that basically means that the voltage drop through each capacitor is going to be equal. So V1 is going to equal V2. And we can't make the assumption that the original voltage is simply going to split. So we actually have to use the equation for voltage, which is charge over capacitance. And since they are equal, the charge on capacitor 1 and capacitance on capacitor 1 is going to equal the ratio of the charge on capacitor 2 over the capacitance of capacitor 2. The next thing we have to keep in mind is that the original charge we started off with, this is conservation of charge, from the 12 volt and the 120 volt and the 6 microfarad capacitor, so this is my Q original, that's going to equal the sum of the charges that then split between the two capacitors. So the first step we need to do, because we can't have too many unknowns and we have Q1 and Q2 that are unknown, is to figure out what this original capacitance is. So the equation for capacitance is voltage times, or the equation for charge is voltage times capacitance. That's going to be 120 times 6 times 10 to the negative 6. And Q is equal to 7.2 times 10 to the negative 4 coulombs. So this is my original charge. In fact, that's my total charge of the circuit based on conservation of charge. So let me change this to T. Okay, because we know the total charge and we're trying to solve for one of the charges for now, we can take the fact that the total charge and Q1 to solve, we can take the total charge minus Q1 to solve for Q2. So we're going to make this substitution, and we are going to simplify this step here. So that's a minus. And try to isolate the Q1. So I'm going to go through this pretty quickly. I've done it in previous problems already, so you should kind of get the hang of the steps to do this. Okay, at this point we can plug in our values. Our Q total from up here is 7.2 times 10 to the negative 4. C1 is 6 microfarads. C1 plus C2 is the sum of these. So 8 plus 6 gives me 24 microfarads, and then when you plug that into your calculator, you end up with 1.8 times 10 to the negative 4 coulombs. The second charge is the total charge, again 7.2 times 10 to the negative 4 minus the first charge, and we get Q2 is equal to 5.4 0.4 times 10 to the negative 4 coulombs. So these are our charges for each of the capacitors. The voltage across capacitor C1 after equilibrium, this is the equation for voltage, charge over capacitance, and for Q1 it's 1.8 times 10 to the negative 4 all over 6 times 10 to the negative 6. The voltage ends up equaling 30 volts, and even though it only asked us to calculate the voltage across the capacitor 1, we know that that's going to be equal to the voltage across capacitor 2 as well. So if you did the capacitance, the charge of C2 over the capacitance of C2, you would also get 30, and you can do that as a way to double check. Okay, what's the difference between the initial and final energy stored in the system of the two capacitors? So the initial energy is equal to just the capacitance, so the equation is 1/2 CV squared. The capacitance is 6 times 10 to the negative 6 for capacitor 1, because all of the voltage is originally in capacitor 1. So if I do the initial energy, I do the full 120 volts, and then I end up with 0.0432 joules. The final energy is equal to the sum of the energy from each individual capacitor. So the first capacitor is 1/2 6 times 10 to the negative 6 times 30 volts squared, and then I'm going to add it to the second capacitor, and then that also has 30 volts squared. To simplify this, because there's a lot of common values here, you can just add the 6 and the 18. So that's 24 times 10 to the negative 6 times 30 squared. And the answer for that is 0.0108 joules. But we want the difference between the two, so the change in voltage is equal to change in energy is equal to U final minus U initial, which is 0.0108 minus 0.0432, and that gives me a negative 0.0324. And the reason why it's negative is because we've got energy lost. So magnitude is all that matters, but the sign implies that there's energy lost. So for part D, it's asking for power. Power is equal to IV, and we're given the current, so that's good. The only problem is we don't know the function for voltage. We're trying to find the power with respect to time, and what we do know is based on our VIR equation that the current is given, and the resistor stays the same. That's also given. It's a resistance of 120 ohms. So I'm going to rewrite my power equation so that I have I and R in it. So that means that the power is equal to I times IR, which is just I squared over I squared times R. So yes, we are going to have to square this function, and that is a negative T over tau. And the the resistance is 120 ohms. The I here is 0.4, but I'm going to square that because the function is squared. And then I'm going to also square the exponent, which is just multiplying together, if you remember from algebra. So if we multiply the constants, we end up with 19.2, I believe. Power is equal to 19.2 e to the negative 2t. The tau is given. That's actually 1.2 times 10 to the negative 4 seconds. And so this is going to be my power equation with respect to time. E is finding the energy. Well, in your equation sheet, and we learned about this in mechanics, power is equal to dE over dt. Change in energy over change in time. We have the power equation with respect to time. So if I multiply the dt to the other side, I have dE is equal to, let me plug in my power equation. And multiply that whole thing by dt. Now from there, we can integrate. I'm integrating from 0 to some arbitrary energy value, and from 0 to, in this scenario, it's saying when equilibrium is reached. We don't know what time it takes for equilibrium to reach, but if we say infinity, then at some point equilibrium is going to reach infinity, or is going to the circuit's going to reach equilibrium and then stay at that same point till infinity. So that's going to be our limits. Obviously, the left side just simplifies down to the energy. And I am going to actually simplify -2 over 1.2 times 10 to the -4. It just makes things easier. That gives -16,700. And I rounded that, but still get a pretty decent answer. So if I integrate e to the -16,700 times t, I get the same function, but I have to divide the -16,700 because that's the derivative of that function, and then I'm going from the limits of infinity to 0. Now, this 9.2 divided by 1600, that gives me a -0.00115. And then when I substitute in my infinity and my 0, e to the infinity minus e to the 0, well, e to the infinity is just 0, and e to the 0 is equal to 1. So if I have -0.0015 times -1, I get positive 0.0015 joules for my energy.